In the previous lesson, we talked about the graphs of relations. In the graphs of relations, we looked at the comparison of how two quantities are related to each other. And we found that if there was a constant rate of change, if the rate of change was increasing the exact same amount, it created a linear function, a linear relationship. And so what we're going to do today is we're going to just focus on these linear relationships, a relationship in which there is a constant rate of change, right? So if you're traveling on the highway and you're traveling 100 kilometers per hour, your rate of change is 100 kilometers for every 1 hour, right? So if I was to graph the distance I had traveled, it would create a linear function, a linear relationship. So when we talk about a relationship, we talk about, whoops, 1 second here. There we go, something's happening. All right, when we talk about a relationship, we talk about different ways of explaining that relationship. And so in the last lesson, we talked about a graph. We can show the relationship by graphing our data. After 1 hour, we have traveled 5 kilometers. After 2 hours, we've traveled 10 kilometers. After 3 hours, we've traveled 15 kilometers. The points fall in a line. That makes it a linear relationship, right? We can also talk about this relationship in terms of words, table of values, set of ordered pairs. For example, let's talk about this in terms of a pumpkin, the weight of a pumpkin, we'll call this the number of pounds of a pumpkin, and the price of a pumpkin. If I buy a 1 pound pumpkin, it's going to cost me $5. A 2 pound pumpkin costs me $10, and a 3 pound pumpkin costs me $15. Right? This table of values explains the relationship between the weight of my pumpkin and my total cost. The rate of change is how much I am increasing by for every 1 unit of pound, right? So I am increasing by $5 for every 1 increase of pounds increase. And you can see that that is remaining constant, $5 per pound. $5 per pound. That is a constant rate of change. Therefore, this relationship is linear, okay? An ordered pair, set of ordered pairs, is really just a table of values, right? It's just written in a different way. Instead of writing it in columns, right, we're writing it as a XY pair. 1 pound is $5, 2 pounds is $10, etc. We can put it in words. The price of a pumpkin is related to its weight. And one of the most powerful, I believe, is the equation. The equation shows the relationship and can generate, the equation generates this table of values or these ordered pairs. This equation generates my graph, right? The equation is derived from those words. So the cost of a pumpkin is equal to 5 times the weight of the pumpkin. And by using the equation, I can talk about all possible input and outputs, right? Because I could buy a pumpkin that is 1.5 pounds. It doesn't have to be 1 pound, and I can keep it in proportion. Oh, well, this pumpkin is going to cost us $7.50, right? Because it's $2.50 for half a pound. And so I can see that in there, I also have points that fall within that, right? And that with that, they all stay on the line. They are all still linear points or functions because all of those points fall right on that line. Okay, so there's lots of different ways to show the relationship between two quantities. Words, table of values, ordered pairs, equation, graph. There's even a couple we're going to talk about a little later in this chapter, mapping and function notation. We'll look at those later. A little bit of vocabulary. Sometimes our data is discrete and sometimes our data is continuous. Let's talk about continuous data first. Continuous data can be measured, and continuous data can take on any value. So any value. For example, up here, my pumpkin could weigh 1 pound, it could weigh 2 pounds, it could weigh 1.5 pounds. It could weigh, there's infinite numbers that fall between 1 and 2. So there's infinite possibilities for the weight of my pumpkin. So it can take on any value. So since there's so many values that fall in between, that's why we draw a line. A line shows that our data is continuous because all of those points in between are also possible values. within our relationship. Whereas discrete data is data that typically can be counted. It can only take on certain values, okay? So for example, if I go back to this pumpkin example, instead of saying pounds, I could say this is the number of pumpkins. 1 pumpkin is $5, 2 pumpkins is $10, so the price per pumpkin is $5. Well, I can't go to the store and buy 1.5 pumpkins. So this is discrete data where I can only buy these certain number of pumpkins. And so if this data is discrete, I wouldn't draw a line through the graph because in between has no meaning. It's just the points. It's still a linear relationship, but it's based on discrete data, data that can be counted. Okay, so here's some examples. A person's height, dog's weight, water temperature, length of wingspan are all things that can be measured. Okay, so that would be continuous data. The number of students in a class, the result when rolling dice, shoe size, number of petals are all things that have certain values only or can be counted, right? The number of outcomes of rolling the dice, right? It could be a 12, 11, but it couldn't be 11.5. Shoe size could be 7, 7.58, but it couldn't be 7.25, etc. So those are discrete data. So again, a reminder when you're graphing discrete data, for example, if I was only graphing the integers of y equals x squared, then I couldn't use 1.5 for x, so then I would just use the dots. If I was using continuous data and I could use 1.5, then I would join all those dots and create a continuous graph. Okay. Another vocabulary word you need to know is the difference between an independent and a dependent variable. The independent variable is usually typically what you select to put into your equation, what you're going to use. For example, how much time are you going to cook your cake for, right? Or how much time are you going to leave the tap on? Or something like that. And so the values of the dependent variable is what you get, the output, right? The temperature of the oven, the amount, the volume of water in your bucket at the end. So your input is your independent. Your output is your dependent. In a table of values, your independent always comes first, and your dependent is always the second part of your table of values. Same thing with ordered pairs. The input, the yellow, are all your independent. The output, right, what you get is all your dependent. In an equation, your output, the circumference of a circle, depends on the radius. The independent is the radius. You choose the radius of the circle and then you calculate the circumference. 2 pi is your coefficient, right? Pi is a constant, it's not a variable. On a graph, your independent always goes on the x-axis and your dependent always goes on the y-axis, right? Your height depends on the time. All right, the last little bit here is linear relationships. How do I know if a relationship is linear or if it's not linear? Well, if it's a graph, it's pretty easy. If it creates a line, it's linear. If it does not create a line when all the points are plotted and the data is plotted, it's not linear. So the graph part is easy. Just look at it. What if I give you a table of values? How do I know if the table of values is linear or not linear? Well, a little number in here. I could graph it and see if it falls in a straight line, or I could just know, well, I know on a straight line that, remember we talked about this last class in a straight line, that if I was to create stairs, each stair would be exactly the same. In other words, the height, the change in y, and the change in x, the change, as you know, I'm going down this many and then over this many, then I'm going to go down the same amount and over the same amount is going to be the same, right? The y as compared to x ratio is going to be the same for every step. Okay, that's what makes it linear. So when I look at this first table of values, which is linear, I can see that's true. I'm going up 3 every time here. Oops, I'm going up 6 there. So does that make it not linear? Well, don't forget, it's not just how much I'm going up in y, it's also as compared to what's happening with my x, right? Or in other words, the rate of change is your change in y as compared to your change in x. All of these are 3 as compared to 1. 3 as compared to 1. 6 as compared to 2. Oh, just wait. 6 over 2 is the same as 3 over 1. So that is equivalent. So that's why this is a linear relationship, because it has a constant rate of change. Where it's not linear is when you're going up by 19, then by 37. Well, maybe it is linear. I have to look at x. I go up by 1. Does 19 as compared to 1 equal 37 as compared to 1? No, that's not a constant rate of change. So that's why the second one's not linear. There's not a constant rate of change. What if it's an equation? Well, all linear relationships have an equation that is degree 1. In other words, my x, my two variables, have a power of 1. So each term, the highest degree is 1, right? So all of these are linear because it has degree 1. This is nonlinear because we have a power of 2 there, we have a power of 3 here, and since it's x times y, that creates a degree 2. So all of those are nonlinear, right? Even if I had x on the bottom, it would not be linear. So let's go through some questions. How can I tell if a relationship is linear or not? So if I gave you all of these ordered pairs, how can I tell if it's linear? Well, remember, ordered pairs are really the same thing as a table of values. So if I create a table of values out of these ordered pairs, I can look at my rate of change. It's easier to see when I line them up. So let's line them up. Let's see what happens with my rate of change. I'm going up 2, so I'm going up 2 every time. Here I'm going up 5. Am I going up 5 every step? Yes, I am. So my rate of change is change in y, increase of 2 as compared to increase of 5. 2 over 5 is my rate of change. Or if I was to graph my line, every stair would have a height of 2 and a width of 5. That's my rate of change. It could be 4 and 10, which is equivalent ratio. By looking at a graph, how can I tell if it's linear? This is not a straight line, so it's not linear. That's as simple as that. How can I look at an equation if it's linear or not? Well, if it's degree 1. That's power of 1, that's power of 1, so yes, this is linear. I know if I was to graph this equation, it would become a straight line. So the question is, how do I graph an equation that I know is linear? For example, y equals 3x minus 2. How would I graph y equals 3x minus 2? Well, you just get some points that work in the relationship. Or in other words, we create a little table of values, right? Just pick any point. Pick something for x. What if I pick 0 for x? Well, if I pick 0 for x, I plug it in, and I get negative 2 for y. So I now have one point that works, 0, negative 2. So go left to right 0, then down 2. I've just plotted that first point. Let's pick something else. Let's pick, I don't know, 2. You can pick anything. So I plug in 2, and I just evaluate. 6 minus 2 is 4. Oh, I have another point. 2, 4, right? 2, up 4. Okay? We can pick anything. Maybe let's pick a negative. Let's pick negative 2. See what happens when I plug in negative 2. So I'm going to get y equals 3 times negative 2 minus 2. And I'm going to get negative 6 minus 2, which becomes negative 8. And I can plot that. So I go left 2 and down 8, 2, 3, 4. And you can see, yes, indeed, these points are falling in a straight line. And if I picked points in between, like 1 or negative 1 or 0.5, they would all fall within that line. They're all points. So these are 3 solutions to infinite solutions to this equation, right? An equation is the rule. The table of values are sample solutions to that rule, or an xy that works in the rule, right? If I plugged in 0 for x and negative 2 for y, I get a balanced statement. So instead of going on and writing all of our infinite points that would work in this, I just have 3 that are linear, and so I'm just going to draw a line through to show this infinite number of points. That means any point along here, I could choose and plug into this equation and it balances. So I can graph a line by creating a table of values, plotting the points, and finishing off the line.